is an excellent way of demonstrating their reactivities compared to each other. You'll find these two videos useful to understand the content covered here. We'll consider the different groups of metals in turn. Group 1, the alkali metals, all react vigorously with cold water. The metal atom displaces hydrogen from the water molecule to form a metal hydroxide and hydrogen gas. Here's the reaction occurring with lithium metal in a beaker of water. Notice how the metal floats on the surface and fizzes quite gently until it disappears from sight. Don't think it has just vanished though, atoms don't disappear. It has formed Li+ and OH- ions, which are dissolved in the solution, making that solution basic. This can be checked with universal indicator paper. What colour do you think it will change to? The answer is blue to purple, depending on the concentration of the solution. If you know the reactivity trend of this group, you react potassium metal with water. Pause the video and consider, then resume. Well, the chemical equation looks nearly the same, but the reaction is much more violent because potassium is more reactive and enough heat is given out to ignite the hydrogen gas, and this then ignites the metal itself. Moving on to group 2, the alkali earth metals, things are a little different. The metal at the top of the group, beryllium, is too inert to react with water. Magnesium just below it reacts only very slightly. But again, consider the reactivity trend. It increases going down the group. The elements below, calcium, strontium and barium, will react with water to form their hydroxides, though in each case less vigorously than their group 1 neighbour. If we drop some strontium metal into our beaker of water, it will sink to the bottom. Small bubbles of hydrogen gas then appear on its surface, showing the reaction is taking place. You might observe a white precipitate, which is solid strontium hydroxide. Unlike group 1, the hydroxides formed by group 2 are only partially water soluble and can often be seen in the solid form as the reaction occurs. The solid hydroxide often forms as a protective layer on the surface of the metal itself and slows down the reaction. But the solution will still be basic, as at least a few free OH- ions are present. Metal hydroxides have many uses in industry. Lithium hydroxide is used to make a highly water-repellent grease. Strontium hydroxide plays a role in the manufacture of table sugar from the sugar beet crop. But you'll never see hydroxides made in industry by adding the pure metal to water. It is far better to start with a salt of the metal, which is easier to make and cheaper to acquire. For example, strontium hydroxide is made by starting with the salt strontium nitrate and adding a strong base, as shown here. What about other metals though, those not in group 1 or 2? In their pure form, the transition metals generally do not react with water. They usually have to give up at least 2 electrons to become soluble ions, and the energy required to do this is just too great. Elements near the border between metals and non-metals, like tin and lead, are inert in water. Molten tin, in fact, is sprayed onto iron cans to stop them reacting with any water contained in whatever is inside the can. Aluminium is an interesting example. The pure metal initially does react with water, but it does so by forming aluminium oxide, Al2O3, and this, much like some group 2 hydroxides, forms a protective layer on the metal's surface, stopping further reactions occurring.